C. All right, so last example, example 6. So example 6, I believe we're going the other way. Doubling times. Yes, another true example. So example 6, the world population is doubling every 35 years. In 1980, the total world population was 4.5 billion people. If the doubling period remains at 35, which is not, find the year in which the world population will be 36 billion people. Okay, so again, doubling times formula, very similar, almost identical to the half-life formula, except for because it's doubling times, there's a 2 in there for the base of our exponent, and we have t over d instead of t over h. All right, so again, n is the end amount that we're looking at, and naught is the starting amount, the time that's gone by that we're looking at, and d is the doubling time that it takes. All right, so in this case, we're starting at 1980. That's our perspective. We're looking at 1980, and there's 4.5 billion people at that point. So that is called our n naught, 4.5 billion. All right, we want to know when the world will have 36 billion people. I think right now we're at about 8 billion in 2020. Now, doubling times, 30 years. Or sorry, 35 years, I should say. 35 billion people. All right, and we want to know how long. Find the year in which that will happen. Okay. All right, so again, I'm going to substitute into my formula, my doubling times formula. All right, so I have 36 billion. And since n and n naught are in the same units, I'm just going to write 36, all right, for billion. My n naught is 4.5. I have my base here of 2. And t, we want to know how long it's going to take. And d is our doubling times 35 years. Okay, so again, this is kind of similar to the example 5. Again, I'm going to get rid of this 4.5. All right, so to do that, I'm going to divide both sides by 4.5. All right, so those 4.5s divide each other out. I take 36, I divide it by 4.5. Actually get a nice number. Even number, no decimals, 8. And again, I have 2 to the power of t over 35. All right, so here's what we got. Now, I want to get at this exponent, right? Because that's what we're trying to solve. So I'm going to take the log function of both sides. So I got the log of 8 equals the log of 2 to the power of that exponent. All right, and just as I did before, I'm going to find the log of 8. Anytime I can find the log of a number, I'm going to do it because I like numbers. I don't like letters and symbols and stuff in there. And so if I take the log of 8, I actually get 0.9. Again, using my log rule, watch out, it's a fraction, so I'm going to write as a fraction when I bring it down. So I have t divided by 35 times the log of 2. All right, again, I'm going to make the log of 2 here. And the log of 2, the log function takes the numbers and makes them smaller. I'm getting a positive 0.3. All right. Again, this is where I always find students get stuck. They don't know how to solve from here, or they make it real complicated. I'm just going to put the 0.3 and the 35 together, which means 0.3 is on the numerator, 35 is on the denominator, so I'm going to divide the two of them. All right, so I get 0.9. If I take 0.3 and divide it by 35, I'm going to get 0.009 d. All right, and again, divide by my numerical coefficient. Both sides. And again, because my t and my d are going to be in the same units, let's see here. Do a little calculating. actually getting right on, 100 years later, our population could approach 36 billion, which means in the year, because this was the starting point was 1980. So in the year 2080, that's if the doubling time remained at 35 years, which it hasn't. That's a problem with global warming and all the food supplies that we need, is that the doubling time of the world population is actually shrinking. I believe to get to 1 billion people happened in like, I want to say 1820 or something like that. It took 100 years, almost or over 100 years, to the population to double back then. So the world population is actually, the doubling time is shrinking very quickly. We're going to run out of room and run out of food potentially. That's what this we'll find out. But if the doubling time did stay the same, we would expect a population of 36 billion in the year 2080. Let's see here. How many decimal points? Okay. Yeah. Any questions there? Okay, so I'm going to switch back because I'm going to look at day 9 here. All right, and so I'm going to switch back on my devices, so bear with me here. Let this dry out a bit. All right, there we go. All right, so switch back in devices. Okay, so let's when is the next test? Why don't we save those questions for later, Diana? But it's in November 3rd. That helps you. Okay, so oh, here we go. All right, so I'm going to present a little again. Again, make sure if you haven't done attendance, do attendance. It's almost 9:30. They yell at me if I don't do it. All right, so I just wanted to go quickly back. So this is our next, this is day 9, our next note. And so it's all about evaluating logarithms. All right, so you have to know what this function, again, I've told you how they invented it, but also want to look at how it's used or what it means. Now, here's the key here for us is that for the exponential function y equals a to the x, the inverse function, inverse is always when you switch your x's and y's, that's what you get. Now, so if we have an equation where it says x equals a to the power of y, this is defined as the log function. Now, here's the key, is that when you look at the log function, the a value is actually your base, the x value is your answer, and the y value over here is your exponent. That's the key today. That's the really weird part. All right, so again, the a is your base, the x is your answer, and then y is your exponent. That's how it's written. Now, here's an example of a function. So we have y equals 2 to the power of x. So what I've done is I've subbed in different x values, -3, -2, 1, and I figured out the y values. And so I graphed this exponential function y equals 2 to the power of x. And over here is the inverse of it, which would be log 2. So I have a base of 2. There's my x value. All right, and there's my y. And so because it's the inverse, all the x's now become y's and all the y's become x's. So that's how you would graph the log function. You can flip it around. Now, what we're going to be doing is I want to kind of play around in day 9 here with using the logarithmic form. All right, so again, I'm going to switch devices. Again, I just want to key in on this fact right here. Whoops. Right here. This is the key here today, where the log function just rewrites the fact that we have the log function is the inverse of an exponential equation. That's the key. All right. So again, I'm going to flip back to devices here. So if you want to do attendance, if you haven't done that yet, let me know. All right. Oh.
Mr. Gates, you're muted.
All right, start over here. Again, when I switch devices, somehow my cell phone switches the volume off, so mutes me. All right, so again, what the question is in example 1a is we have 7 to the power of 2 equals 49. That is written as exponents exponentially. All right, we want to switch it to a logarithmic function. And so I'm writing the log, but again, the base is the number that goes right here. So 7's our base, goes right here. Our answer goes right here. And then it's equal to our exponent. So what it's saying is 7 to the power of 2 equals 49. Now here's a little bit of a thing. Is in day 8, when I was solving, you notice how I just wrote log? You never saw the little number? Because it's always 10. If you don't see it, there's a 10 there. So on your calculator, it's a 10. All right, but when we have a different base other than 10, then we have to write it in there. All right, so that's just that question written as an exponential. I'm going to try B here. What do we got? 5 to the power of 3 equals 125. So that's written as an exponential equation. I want to write it as a logarithmic. And so again, I'm going to write log. The base of 5 goes right here. So that's telling you what the base was. The answer is going to go right here. And the answer is a 3. So what the logarithmic function really is saying is, if you have a base of 5 and your answer is 125, what would the exponent be? 5 to the power of 3 would give you 125. That's what it's saying there. Example 2. Go the other way. Flip-flop. And so now I have the logarithmic function. So I got 4 is equal to log of 2 and 16. So I'm going to write it in exponential form, which means there's my base. There's my answer. And what would the exponent have to be? Right here, 4. So there is it written in exponential form. All right, B. Let's see here. We have 4 is equal to log of 3, I believe, down below. Yep, 81. So again, if I want to write it in exponential form, there's my base. There's my answer. And that's the exponent I would need to make that happen. So 3 to the power of 4 would equal 81. All right. Let's see here. Example 3. We have evaluates. We're actually going to figure something out here. Log of 4, 16. All right, so we're not just changing the forms here. We're actually figuring out an answer. And what that's saying is, here's my base. Here's my answer. Oops, let's get rid of that. What would the exponent have to be? 4 to the power of what would give you 16? Well, that answer is 2. 4 to the power of 2 would give you 16. Let's see here. B. We got the log of 5 in here. 625. All right, so again, what it's saying is, here's our base. We don't know this value, so I guess I'll call it x, is equal to 625. All right, and I believe the answer, because I know 5 to the power of 3 is 125, do one more. X is equal to 4. All right, so again, just getting comfortable with the notation. I'm getting emails here about doing my emails, or about doing my attendance. So I'm going to move down to equation number or example number 6, all about the Richter scale. Again, true values, true science. So let's see here. So I'm going to do example number 6. All right, so let's see here. The old Richter scale is used for measuring the magnitude of an earthquake. I think most of you know that. The Richter scale magnitude is given by this huge equation here. So let's see here. R, so that's going to be your Richter scale number, is 0.67. Again, this is a real equation. Log of 0.37 E. And what's E all about? I believe it's the energy in kilowatt hours plus 1.46. All right, so in A, I'm not going to do A because, again, time, and it's not that crazy. An earthquake releases, well, obviously a lot of energy. That's why it can be so destructive. Kilowatt energy. So in A, all I did was plug in the values and then figure out that it was an 8 on the Richter scale. But now I'm going to look at B. B is how many kilowatt hours of energy would an earthquake have to release in order to be a 6.5 on the Richter scale. All right, so there's our Richter scale number. What we want to know is the E. So we're going to solve inside the log function. All right, so the first thing I'm going to do is I'm going to plug in a 6.5 in for my Richter scale number. I just wrote it out. All right, there we go. So I plugged in my Richter scale number 6.5. I'm going to solve this equation. The easiest thing I can do right away. Move the 1.46 over to the other side, which means it's going to be subtraction. I get 6.5 minus 1.46. And again, writing out the rest of it. Now, again, something I usually always have to bring up here. When I have the log of 0.37e, they're not multiplying. That 0.37e is in the function. It's like the sine function, the cos function. It's in there. It's not multiplying. Log isn't a number, so you can't multiply. Let's see here. So I get 6.5 minus 1.46. I get 5.04. Now, one thing I always say in math, if things are getting more complicated, bigger, you're probably going the wrong way. See how things are getting smaller for us? Good stuff. I'm going to get rid of this 0.67 because it is multiplying the log function. I can divide both sides by that 0.67. All right, so that chops them off. All right, so I get 5.04 divided by 0.67. I'm getting 7.52. Log of 0.37e. All right, now here is where we are going to use the definition of a log function, its relationship to an exponential equation. All right, so see how the log there is. Because there's no number down here, it really means there's a 10 in there. So again, there's my base, there's my answer, and there's my exponent. So I'm going to take this logarithmic equation right now, and I'm going to write it in exponential form so I can solve it. So I've got my base here is 10. There's my exponent of 7.52. equals my answer, which is a 0.37 E. And again, E stands for how much energy is released from the 6.5 earthquake. Now, if I take 10 to the power of 7.52, here's the number I'm getting. 3, 3, 1, 1, 3, 1, 1, 2.15 is equal to our 0.37 E. Then I'm going to divide both sides by that 0.37, right, by a numerical coefficient. And the energy released from a 6.5 is 89,494,897.7 kilowatts per hour of energy, which is crazy amount of energy. The average house in a day uses or in a month, the average house in a month probably uses about 1,500 kilowatts per hour of energy. This one's using 89 million. That's released instantly. All right, so that again is exponential equation. That's day 8, 9, logarithmic functions. Because we're running a little long here, I'm going to start the next lesson at 10:05. Okay, 10:05, which we'll do day 10. If there's no more questions, or if there is any questions, let me know. Okay. I better do attendance. Snapping on me, huh?